Alright guys, so today we are going to do problem of the day for December 11th. This is problem 124, binary tree maximum path sum. I don't think I've ever attempted this problem, so this will be the first time I'm looking at it. Let's go ahead and get started. It says a path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum of a path is the sum of the nodes' values in the path. Given the root of a binary tree, return the maximum path sum of any non-empty path. So we have 1, 2, 3. And it says the optimal path is going from 2 to 1 to 3, and you'll get the path sum of 2, 1, 3, 6. And then here we have the maximum path. We have a negative number, and then we have a few positives. And then we say, okay, go 7, 20, 15 is 42. That is our maximum path. All right. So, as always, let's clarify what we mean by what the goal of the problem is. So the goal of the problem is to find the max sum of a path in the tree in which it does not cross over with itself. So our params were given for input 1, the root of the binary tree to quote-unquote traverse. Okay, output, return, this is inputs, this is param 1, things of bookkeeping. Okay, return the integer max sum of the max path in the tree. Okay, so that makes sense. Now the question is how we're going to do that. Let's take a standard tree, for example. So very simple. 2. Let's push this over here. 2, 4. And then we'll have 3, we can do 5, -5, 2. So we have a couple paths we can go. We can go from 3, 2, 1, 4, 2. We can go 3, 2, 1, 4, -5. We can go 5, 2, 1, 4, -5, 5, 2, 1, 4, 2, or we can even do subpaths, so just 5 to 2, 5, 2, 1, 3, 2, 1, 3, 2, 1, 4. You know, we don't have to go through all the numbers too, so that's going to be quite an issue. And considering the fact that the binary tree is not sorted in any way, for example, all the nodes to the left must be smaller than the middle node, that's certainly not the case. Okay, so the question is, how do we calculate this? So kind of going off our example here, first thing I notice is that on the left side of the tree I start with the children and I go upwards, and then when I go from the root I always go down and to the right. And then all these values, I always go down. So that can be kind of our sequencing. Sequence is that left nodes left of root, go upwards. Well, not necessarily, right? What if it doesn't really matter which direction it goes, it's just that if they're connected in a quote-unquote path. So this is kind of, I can see some dynamic programming here in which you're saying, okay, if pretend I went into a sub-problem, okay, and I pass in only this 3, well, the best path starting from this node is going down 3. And so when I start at this path 2 now, I have 2 paths to go to. I either go to the 3 or the 5. And so I pick the 5, okay, and then I go up 1, and now I can choose to go down this path, And I can go down this path, right? Well, that's the same for this path as well. For any node here, I can go down both paths. Okay, so each node, you pick the best of these three paths. So this is a DP problem. And at each node of the DP problem, you pick one of the three paths, right? Go down the left, go down the right, go down left and right. So for max sum, go down left and right, but when returning for the DP solution, only pick left or right. So what I mean by that is that, say I'm at this 2 node, right? I know for any of the ancestors going down the 2 node, it can only go left or right. It can't go 3, 2, 5. But I do know that 3, 2, 5 is still possible, and I need to account for that by recording that as the max sum. Does that make sense? So for example, I calculate 7, 15, now I go to 20. I know that if I'm going to receive 20 from like here, if I'm going to make a decision to go to 20, I will always go to the 15 because it's bigger. However, for the max sum, I'm also going to account for this U shape I make going down both paths. And I just repeat that process. I go to -10, I can go to the 9, the 20, or I can go to the U shape. Actually, we know that we just have to pick left or right each time we go down a node, and we save that value so that we don't have to traverse that again. And then we, of course, add all these together, left, up, right, because we know that the best solution is always going to be left, up, right at any point in the tree. At some point in the tree, it's always going to be left, up, right. Whether that's just a leaf node by itself, left is none, up is 15, right is none again, that's fine. Or, for example, left, up, right here. Or, hold on. Or it's the value by itself. Suppose we had a completely negative tree, right? So -1, -2, -4. In this case, it wouldn't be left, up, right. It would just be the value by itself. Excuse me. Also, pick value by itself. Okay. So that's kind of the pseudocode. Oh wait. What if it's like this? So then we wouldn't go left, up, right. We would only go up, right. Okay, so for max sum, so for each node, you pick the rest of the 2 paths to return as DP. Go down left, go down right, go down neither. And then for the max sum, pick the best of these 3. So go down left, go down, go left, up, then right, go up, go up, right. So instead of saying up, I'll say current, So you can go left current, current right, go current, or yeah. So that's all the possible quote-unquote paths you can make at that very moment. Current, right plus current, or go down just current. Right, for example, this 15, I just pick current. Here, if this was a -7, I can go left current and pass that up. I could go right current and pass that up, or I can just go current and pass that up. So if this was 11, then I know that left current then right would be better than just current right. And then I would be able to do that. Okay, so it's kind of like a DP problem. What is the time complexity of the solution? Time complexity. This could be O of n, where n is the number of nodes in the tree. Space complexity, since I'm going to create a completely separate tree where I have these sums, right? Remember these nodes where. So I'm going to create a completely new tree with that in it. Okay, so let's go ahead and make that. Tree node root sum root. This is similar to the problem we did just yesterday, I think. So we have that. We have our new tree node. And now I need to create that optimal path. We'll have int result. We'll have result equals 0. We'll have int DFS. We'll take in tree node current and then tree node current sum cur. So this is the tree node with the current sum. So we'll DFS root sum root. This will be void. Okay. So what I want to do, of course, I want to DFS all the way to the bottom. So if cur left, DFS cur left. And then we'll have a new node. So tree node left, sum left, so put a new tree node. Okay. Then sum cur left is equal to sum left. So sum left. Okay, so we'll df that in. Then same thing, if there's a right, if cur right, we'll call it sum right. Right, so do sum right, df's that bad boy in. Okay, now that there's no, we've handled the left and right. See some curve value, some so this defaults to 0, right? So some curve 0. We'll say some curve What is the minimum integer? CPP min integer. Int min, right? Int min. I can use that, right? Int min. Max sum current value. Okay, left current. How about this? Some curve value. Some curve. Or curve value plus. What was it? Curve value plus left. Some left value. Okay, and then same thing here. This is some right. Okay, and then we will, once that is handled, then we need to take the max sum max of result, left current then right. So that would be some cur left val So basically, I'm following that algorithm I wrote down there. So cur val is here, left cur. Left than current, current than right. So max results, and this should be min integer. So it should be the max of the result. The curve value, this should be cur val. So cur val by itself. With these four, then current right, then left current. So this is cur left with some left val. If cur left and cur right, then this is for the max cur val plus some cur left val plus some cur right val. Okay, so just as we talked about, the DP to return, for example, if I'm here, if I'm going to return, so I'm going to return this as the max, that's fine. So I save this as the max here. Okay. But when I come up here, I can't do 1527. I have to go 2015. So that's this. And that should be it. Fairly straightforward. Let's give it a run. Okay, no min integer. Oh, it's int min. Int min. Let's give it a run. I guess let's make sure it works first. So going through this in the example, I pass in -10. In my new tree, I know it's just the left one, so I create a new tree node, connect it, pass it in. Okay. then I DFS here, and then I notice that it doesn't exist. There's no left or right nodes. So then some cur is equal to cur value. That's fine. Come back up. Now I pull that value, and I say, okay, now my sum cur value here is going to be the max of -10 or -10 plus 9. And so it's -1 now. Now I go to the right, and I DFS, and I DFS again. Now it's 15. Now this is 7. This should be 35. However, I notice my result is going to take into account all 3 of these nodes. So then I save that to result as 42. And then I pass up 35 up here. So this sees 35. So obviously then it says, okay, now my new max is 25. Let's see if that's my new result. If it's not, whatever. And now I try to, do left, current, right. And then my result is 42. Okay, so that should be that result. Let's make some new test cases where maybe it's just a single node, or maybe it's a bunch of negative integers. So there's 1, -5, -10, and of course, let's make a new case where perhaps it's only 2 integers. Okay, and that should be it. We're going to post the result, see our answer. It beats about 64%. The memory is about 5.24%. So that is problem 124. Let's take a look at the solutions. And let's look in particular in C++. O of n solution. Yes, DFS. It's treated unidirectional, cannot retrace. Yes. So basically, same idea that I had, except a little more cleaner. Use the integer instead of having to create a new tree for that. So that's something I could have thought of. But basically the same idea. Yep, adding them and doing a post-order traversal. Okay. So cool. That is problem 124. Hope you learned something from that. And hope to see you next time.